Hi everyone, thank you all to join the talk for this 5-week e-poster about the subject of efficient deployment of deep learning models. This study has been carried out by Florian Chouteau and myself, Hugo Vazquez, and all the computer vision team of Airbus Defense and Space at Toulouse, France. The computer vision team is composed of dozens of engineers and breaks its activity in two principal axes. The first axis is vision-based navigation, which uses optical sensors to get precise localization information. The second axis is about semantic information extraction and is mainly related to data sciences. Why do we need efficient deployment? The challenge is to design a deep neural network without knowing the platform on which it will be executed. However, nowadays, the main solution is to design and train a network for each use case. For example, for a platform with high computational resources as ground segment, we will design and train a big network. For small computational resources as satellite and nanosatellite, we will design and train again a small network. However, this method is expensive in terms of engineering work and energy consumption. So, what is the solution for efficient deployment? The main idea of this work is to train a single large network dynamically, that we call FSNet, with many way out, each way out corresponding to a subnetwork matching specific computation requirement. For example, here we have an initial network, FSNet. We will train it in a specific way that we will describe later. Once the training of FSNet is done, we can extract from it specialized network matching specific hardware target. The main idea is that we only need one training to get a large family of network. So, what is the methodology to train a FSNet? First, we need to design the network design space, which means define parameters enabling efficient way out for each subnet in FSNet. For each kind of architecture, as VGGNet, ResNet or UNet, we have to define a design space. For example, for VGGNet, we choose 3 degrees of freedom: the depth of the subnet that we want, the number of filters on the first layer, and the expansion coefficient. We enter this parameter and we get a subnet in the family. Then we have to manage the weight sharing. Regarding the network depth, if we want a subnet with D layer, we keep the first D layer in the FSNet. Regarding the choice of filter in a layer, the selection is done according to the following procedure. For each filter, we compute the L1 norms. Then, we keep the M filter, if we want M filter, with the highest L1 norms value. Finally, we need to manage the dynamic training. The main idea is to sample subnets in the design space from largest to smallest progressively, and we accumulate the gradient of several subnets at each batch step. Algorithm 1 gives the pseudocode for one epoch training. I encourage you to look at it carefully later on if you want more details. Now, I will present results for 2 use cases. First, application to land cover classification with the Eurosat dataset. The graph on the left highlights Eurosat top 1 accuracy according to the Mach number. Each point on the green curve is a subnet in the FS-VGG family. Each point on the blue curve is individual training, which means that all network has been trained from scratch and independently. One may observe that our method can generate with a single training a family of networks that perform as well as if they were trained separately. Then, we address the problematic of segmentation with cloud detection task on Sentinel-2 CloudMOS catalog with UNet architecture. One may observe that we are able to generate a large family of networks with different performances. The images with CloudMOS illustrate this difference of performances. This project can be integrated in different phases of a spatial project lifecycle. To name a few, fast delivery of precise information about the trade-off between operational need and our design, fast delivery of prototype, and at the end simplify deployment and reduce costs in case of cross-platform target. Further improvement can also be done as training a a latency accuracy predictor. At this point, we generate a family of networks, but we don't know the one that will perfectly match with our target. So, it is possible to train a predictor to find the right one. Thank you for watching. I was very excited to work on this project and I hope to see him developed. Please feel free to email us if you want to find out more.